Good morning. Thanks for coming. Hope you have a good time so far. I'm Emily Jiang. I'm an IBM developer.
And I'm Clément Escoffier. I'm working at Red Hat as a software engineer and architect.
So once upon a time, there are two microservices.
Wait a second a minute. I've seen this scenario thousands of times over the past few years, and it never really worked well. Can you tell us a little bit more about A, B, and actually how they're interacting?
Yeah, A is awesome. A runs on OpenLiberty with the color of blue. And B runs on Quarkus.
Oh, cool. That's pretty cool.
And they interact with each other. So when a customer comes in, they directly invoke A, and A call B, B responds to A return response to the customer.
What you forgot to mention is actually B is a password generator, and if you find the logic behind this generator, you will be able to discover Emily's and my password. So be very look at the code. So you are telling here that A is calling B, but that's a synchronous invocation, right? How does that work?
Yeah, exactly. So basically, this is a customer log to the browser and directly poke the service A URL, data client test hello. And then in that, HTTP GET and directly call the backend and B/service/hello, and B responds, and then A responds back to the customer.
So you have an HTTP request, and you get the result in a synchronous manner, so you can use it. But you know, there is one thing trendy these days is becoming asynchronous. Can we do that?
Of course. We have asynchronized from microprofile for tolerance. You can do this. And also, there's asynchronized from the microprofile context propagation. You can get an executor, and then you can launch async.
So basically what you're saying here is that instead of calling my service B in a synchronous manner, I can call my service B using this asynchronous construct. So okay, to get my result, I will get my result inside the callbacks, but yeah, that's how asynchronous works. However, well, I have lots of questions about asynchrony. We are going to come back to that later. But yeah, there is one thing that you need to know with microservices is that, well, they're like kids. They misbehave most of the time. At least it's the case of mine. So we need some kind of mud guards. We need some kind of way of protecting ourselves about all this misbehavior. Do we have anything in our toolbox to do that?
Of course, I have a secret weapon, which is a microprofile for tolerance. This is exactly created to make your microservice resilient. So for misbehaving case, and then I have this secret weapon. Automatically, for example, if the service B is not behaving, I have a fallback. If service B overslept, I time it out, so I can still return to the customer with a meaningful result.
That's pretty cool. Is there anything else? Because here I see a fallback, I see timeout, but do we have anything else?
Yes. We have retry. This is retry is to fix the scenario, you know. If something not working, the first impression, try it again. So this retry automatically fixes the intermittent problems. So you can even configure how many times you want to retry, and with some delays, how much time you want for this whole retry. And also, you don't want to run into a situation it's repeatable timeout or repeatable errors. So we have a circuit breaker. Basically, after some times exception and etc., the circuit is open. You will return, so the service can return to the customer straight away without the customer need to be timed out. So this is circuit breaker. And in circuit breaker, you can specify the criteria. When what's the rolling window and how much percent of the failure, and then circuit will be opened. And then with some delay and retry, get one request through to see whether it's success or not. The third one is the bulkhead. Bulkhead is manage the concurrent thread. So basically, you don't want to utilize the whole thread and consume all the resources for one particular microservice. In these circumstances, I only allow at maximum 5 concurrent requests can be executed, can invoke my service A.
So, okay, so we can limit the concurrency with bulkhead, but again, we want to have some kind of asynchronous interaction. And there's one thing that always happens as soon as you switch thread or as soon as you do asynchronous is that you are losing your context. Let's imagine that I log into our service A, and so I have a principal that is stored in the request. But as soon as I call my service B, and then the answer comes back, as I am on a different thread, I'm not there. My principal is not there. So what can we do about that?
Yeah, this is an old problem. Like since the beginning, when you do multi-threading, you have this issue. But Java EE fixed it, partially. Like Java EE, you have a manager executor, and it can propagate a security context, and etc., on a JNDI or this context. However, you are right. Like a CDI context and also like transaction context, you wish to propagate it cannot do that. With that, we have microprofile context propagation. It allows you to capture this context. When you start a new thread, it pushes the context to the new thread. So you got all the context you need to do the work.
Okay, can we see an example of this?
Yeah. So in this example, use the thread context. So you can directly get from the microprofile context propagation. So you can use this builder pattern to get a thread context. When you launch a new like asynchronous call, you use this thread context and with the context captured. So this operation, this task will use the context being propagated. So it will run in the correct context.
So that means that in my callback, my user principal has been restored, which is kind of cool because I can continue my logic based on this.
And also CDI context will be propagated as well.
So let's go back to those asynchronous calls because, well, I've seen a lot of asynchronous things over the past few years. It's actually my kind of things. But there is some misunderstanding that most asynchronous things we see, they aren't non-blocking. They basically just offload the job or the work to another thread pool. And here there is something that we need to discuss. Thread pools. Yes, they are not really, let's say, cloud native or whatever. When we delegate to a thread pool, basically we need to customize this thread pool. We need to tune the thread pool. But how many threads should we write? How many threads should I have here? Should they be created immediately or so on? It's actually a lot of questions. And there is this new kind of things, non-blocking IOST, that may help a lot with this. So when you use an asynchronous API, check whether it's actually just thread pool or it's really non-blocking. Because with thread pools, we are going to create threads, and then we have an issue. Each thread has a memory cost, a lot, between 1 and 4 megabytes. In a container, well, while we was outside on container, on bare metal, on very huge and large machines, no problem. We had as much memory we wanted. So no problem with this. However, now we are going to deploy our application into containers. Who is using containers here? Almost the full room is using containers. So as soon as you use containers, you need to understand why you do that. You don't do that to isolate the port 8080 that is used by 2 of your applications, even if everybody is doing this. You are doing it because you want to increase your deployment density. You want to have one machine with a few CPU cores that will run more than one application. Even on the cloud, even on Amazon, Azure, or whatever, there is somewhere where there is CPU cores that are going to actually execute your workload. So when you have a set of containers that you deploy on your container host, like these 4 containers here, if some of these containers are using a lot of threads because that's the concurrency model they use or because there is a lot of thread pool and so on, their memory pressure is going to increase. Their memory consumption is going to increase because every thread has a memory cost. It's not the only cost you have when you are using too many threads. There is also a CPU cost. Because more threads you have, more time you spend switching between threads. That makes sense, right? Even if this time has been reduced over time, it's still not zero. And, well, if you are using a cloud provider, you are paying for this cost. So we need to find some other way of doing this. You can say, yeah, but no problem, Clément, I can use quarters. One cool thing about containers is that when your application reaches a quarter, they're just killed. Simple. Which actually saves the resources as they are free after that, but yeah, it's not necessarily what you want. So when you use non-blocking I/O, you can save a lot of threads because actually, well, the same thread can handle a lot of different requests, and it's all delegated to the operating system to manage all the non-blocking aspect, and then you will be called back. So this is kind of a new model that will save from those thread pools. So what we really need is not only being asynchronous, it's also being non-blocking to use our resource efficiently. And it's become a big issue on the cloud, because on the cloud, resources are very expensive. There is a good chance that your host on which you run your application is closer to the power or to the configuration of a Raspberry Pi than from your laptop. Imagine deploying your application on Raspberry Pi. Think about that for 1 sec. It can be slow, no? So we need to think about this. So what do we have now?
Yeah, so we have the asynchronous, and we have fault tolerance to build the resilient microservices, and then we have context propagation and make sure all the contexts push to the new thread. And also we have a non-block I/O. It looks okay, right?
Well, not really. There is a few things that we didn't cover yet. Typically, service B may be away, may not be there, misbehaves. So, okay, we have fallbacks. Granted, so we can provide a meaningful answer to our users, but all the request has been lost. So what the user will do? The user will retry, push F5, so you are going to even do more requests to try to increase your concurrency. So that's not going to work so well. Second thing is that you may overload service B with too many requests. So we need to find some other way of doing this.
Okay, then let's go reactive. Let's take a look at reactive then.
Yep. So, yeah.
Yeah, I did a lot of research with reactive. So it's you got a reactive programming, you got reactive extension, and then reactive system, reactive streams, and reactive manifesto. And also you heard of RxJava and Spring Reactor, Arca. Gosh, it's so many things. I think we need a PhD to understand this.
So the good news is that it seems that I have a PhD, so I can draw some arrows like this and make a little bit out of sense of this. So it all started with the Reactive Manifesto, which tried to define an architectural style to build responsive distributed systems. A distributed system, reactive system, is going to use messages as the main way to interact with its peer. That will provide us elasticity and resilience, but it comes with one main idea that everything is going to be asynchronous. So we need a way to write asynchronous code. This is where reactive programming comes into the game, and we can have a different way to do asynchronous code. You can use actors, fibers, events with callbacks, even spreadsheets. Who is using spreadsheet here? Microsoft Excel or whatever? Not that much. We don't have managers in the room? Okay, well, actually, spreadsheets are a way to do reactive programming because when you update a cell and you have a formula, the formula is updated automatically. So there is some kind of reactive there. The thing is, when we do reactive programming, we need to have the concept of streams because we have a sequence of values. That are the values of my cell. First I have 1, then 2, and so on, and so on, and so on. So we will see that what it means to have a reactive streams, and then we have reactive extensions that implement reactive streams with operator and so on. But it's still not very clear, right? I could do better.
We need to do a little bit more.
Yeah, so let's start with reactive programming. Reactive programming is about data streams. We have streams of data where you will have data items or completion signal or the failure signal. This main idea is a propagation of change. You are going to observe a stream, and as soon as you have a new item, a failure or something, you are going to be notified. And you are creating a new streams and so on and so on and so on. On top of this, we need to have reactive programming that will help you write things using data streams. So it will come with reactive types and a set of operators. The set of operators is very important because it's how you are going to write your software, your pipeline. So then we have reactive streams that come with a non-blocking and asynchronous blood pressure protocol. It's a little bit on the side here because there is some glue to make things work all together, and it's where we have reactive extension libraries such as Java, Reactor, or microprofile reactive streams ops that implement the reactive streams blood pressure protocol that provide streams type. They use different names depending on the library, a set of operators, and we will be able to implement our reactive applications that way. So, did you know this, Emily?
Yeah.
The Flow API?
Yes, I follow the JDK very closely. And I know in the JDK 9, we introduced a class called Flow. And with the 4 interfaces, publisher, subscriber, subscription, and processor. Actually, this, if you know org.reactives, you will be pretty familiar with this, right? Because the Oracle come to this reactive party 7 years later, they all played like happily together, and the Oracle saying, right, we need to standardize something. Okay, and then what do you feel if you have been working 7 years and then work on org.reactives, and you will say, okay, we are doing our own thing. However, Oracle saying, okay, I'm going to introduce the first interface called subscriber. And then publisher and subscription and processor basically is identical copy to the reactive streams.
Well, in the meantime, they remove the author tag. But
yeah, and then Rx, Java, and Spring Reactor, we love it. They all implemented. So basically, for these interfaces is very simple, like a publisher, so you can get observable associated with the publisher. And a subscriber, if you think about it, is a consumer. So consume messages, and then on next will be called if it's a new item arrives, and then on error will be called if an error arrives. Remember these reactive streams. You have 3 channels. One is subscribe, the other one is data, and then error. So it's and then the error will go through error channel. And then incomplete will be called publisher say, I'm done with, and no more data for you. And then subscription is very important. So here is like a request with taking in the number. So this reflects the back pressure. And then is cancel means, okay, my subscriber, I have no interest in this publisher anymore. I want to cancel it.
So basically, you say that we have publishers, which will be our source of data, subscribers that will consume those data, and then you mentioned processors, which are basically having the 2 roles, so they are just extending both publisher and subscriber.
Yeah.
So let's have a deeper look on how it works. So you have your publishers, and you have your subscriber. The subscriber is going to subscribe to the publisher. Fine. That's how you will do it. Then you will get a contract back. That's what we call the subscription. This is key, because the subscription is where you can ask for data. That's the requesting. For example, when the subscriber is ready to handle data, he will say, yeah, give me 3, because I know that I can handle 3 data at that moment. It could also say, give me long.max, which will be unbounded, but generally it's better to use a bounded number. After that, the publisher can emit these items, at most the number of items that has been requested. Something to keep in mind is that the request may happen in one thread or in one flow, and the item, the onNext method, can also happen in another flow. So there is really asynchrony here. So the publisher is going to call onNext on the subscriber with the first item, onNext on the second item, and then if the stream is completed, then it will call onComplete. Obviously, as soon as you have failures, it will call onError with a failure, and then no more data will be sent. If the subscriber don't want data anymore, got too much, and so on, it can just cancel the subscription, which normally should release all the resources used by the publisher.
Yeah, I mentioned earlier, you also have a processor. Processor can talk directly with the publisher, so get a message from publisher and then send a message to subscriber. Itself can deal with both the publisher and the subscriber.
So one thing to really understand about streams is that nothing is going to happen until you actually subscribe. And actually, it's even more lazy than this. Nothing is going to happen until you subscribe and you request at least one element. Of course. So it's really, really lazy. And these request patterns will flow from your subscriber to the next processor, and so on, until the publisher. And each processor can decide to handle the back pressure differently, but generally, it just passes the requests upstream. So there are interfaces, publisher, subscriber, and so on. And you may have the idea, say, hey, they look simple. Come on, they fit all in one slide. I can implement that. Don't. Don't even think about it. You will have nightmares. The interface are simple and fit on one slide because I removed the Java doc, by the way. But the TCK that come with this is very, very strict. It's actually really checking that you're implementing the non-blocking asynchronous back pressure correctly. And fortunately, there is many libraries today that implement that for you, such as Project Reactor from Pivotal, where you have two types, Flux and Mono, that implement publisher. You have Eric Java 2 that has one type implementing publisher, which is Flowable, which is equivalent of Flux, more or less. And we also have microprofile reactive streams operators that provide a smaller set of operators, but you can create things like this.
Yeah.
How do we use it? Well, for example, in my second snippet here, I can create a processor where, so a processor is this man in the middle kind of things. I will get messages, and I will process my message using the map operators or another maps, and then do some asynchronous operation using a flat map completion stage, and the result of this will be passed downstream. So that's the type of operators you have. One thing is there is many operators. I think in Flux, they have something like 400 methods or things like this, so 400 operators. Map and flat map are the most important one, especially flat map. So as soon as you understand flat map, you more or less understand all of them, but it requires some time. It's very functional, as you can see, so there is a big of a gap to manage that. But one of the great advantages of the libraries, you don't manipulate the subscription by yourself. You don't manipulate the back pressure by yourself. And this is key. Those libraries are doing that for you.
Right. So you are saying right now, like even GDK 9 has this reactive APIs. In order to use the API, you still have to choose either your favorite implementations, such as XJava or Akka or Spring Reactor, or our microprofile reactive messaging, reactive stream operators, right?
But as they all implement the publisher, subscriber, and processor interface, they are all interoperable. So you can have part of your code using Reactor, another part using Eric Java 2, another part using reactive streams operators. That will just work because it's the same contract behind the scene. It's interfaces. So that's cool to have this interoperable level. But yeah, we digress a little bit, right? How does that is going to fix our two microservices and our password generator?
Yeah, I really want to create a reactive systems. I want to create a reactive microservices.
So the thing is, you don't really want to create a reactive microservice, Emily. What you want is to create a reactive system based on reactive microservices. Reactive systems has been defined in the reactive manifesto that you can check out at this URL over there. And it has these 4 pillars. So it's an architectural style to build responsive distributed system. The main idea is that all our entities, all our microservices are going to exchange messages.
Yep.
Those messages, because they are sent to virtual addresses instead of direct endpoints, we can have elasticity and resilience pattern. Elasticity because we can have 1, 2, 3, and subscriber behind it. We don't care. And resilience, because if one of our subscribers fail, well, there is probably another one that will take over and continue the processing. If you have, depending on the message technology you use, you may even have acknowledgement, retry, and things like that, publish, subscribe, and so on. So you can have a really broad set of possibilities here. If you're able to handle the load, handle the request, even on fluctuating load, and even when facing failures, you are providing a better service to your users. You are becoming responsive, and you just implemented reactive systems. One thing to keep in mind is this asynchronous message passing over there. To make this to work, all our microservices will exchange messages in an asynchronous and non-blocking manner. This is going to fix a little bit our two microservices here, because we are going to introduce temporal decoupling. What's temporal decoupling? If you have A and B is not there, you are losing your request. Yes, you have a fallback and so on, but all the requests are there. So there is some kind of strong coupling between your microservice. The main idea behind microservices is to have loose coupling. So HTTP is not really great for this. The second thing is that we need to have a back pressure protocol in the sense that we don't want to overflow B with too many requests. We want to have B in a good shape and so on. So we want to do this actually. So send messages using virtual addresses, so we can have 1, 2, 3B, whatever. The messages can be durable to avoid the temporal coupling. We will use non-blocking IOST. So okay, we start seeing how we are going to implement our reactive systems with this and using microprofile specification.
Yeah.
Can you tell us more about this?
Yeah, I know messaging is an old concept. For example, if you really want to get people to do something, you send them emails, right? You guaranteed, okay, when that person gets an email and do it. So similarly, the microprofile reactive messaging want to build a kind of loosely coupled. So I could basically publish my message, and then consumer can be lazily consume message and whenever they want, they feel like it. So basically, so here is like very loosely coupled, and then you can do the message and send it to the messaging broker, and the broker can store the message and then make sure the message is persisted, and then the consumer can come in at any time. In this way, you could do sometimes asynchronous, and sometimes you do the messaging based.
So on the left side, we will have our microservice A, on the right side, our microservice B, and they will interact using this microprofile reactive messaging technology.
Yeah.
So what we will have is that we will have A, that actually here is on the right side, that is going to publish messages using the @ongoing annotation. So @ongoing says that, okay, I'm going to produce data on the channel name channel. Channel being a virtual address. And on the other side, so B will consume this data from the channel and get some data and process it and so on. If it will be a processor, it will not only have incoming, but also outgoing to say, okay, I'm getting some data from here, I'm processing it and writing it to another channel. But that can work in memory. But how do we do that with a broker, right?
Yeah, exactly. I think it's in production, obviously, we need a message broker, right?
Well, we don't need a message broker. We want to be cool. We want to use Kafka.
Yeah.
So let's do that with Kafka. So, well, here, what will happen is that we will have a connector, a reactive messaging connector, that is configured to map a channel to a specific Kafka topic. On the other side, it's the same connector or different connector for the same technologies that will do different mapping, so from a topic to a channel. The connectors, here we're going to use Kafka, because of course we're cool, but you can use MQP, you can use MQTT, you can use WebSockets, you can use even emails, Amazon SNS, and so on and so on. So there is a set of connectors, and depending on the implementation of reactive messaging you use, the set of connectors might be a little bit different, but because the connector interface is part of the spec, even if they are not implemented with your implementation, they will be compatible. One thing to keep in mind here is this. We have back pressure. So that means that when we are writing to Kafka and when we are reading from Kafka, we are managing the reactive strings back pressure in a non-blocking and asynchronous manner because we want to pass the TCK and so on, which means that actually we have end-to-end back pressure here based on Kafka. It will work the same way on MQP and so on and so on and so on. So we are developers, Emily. We need to show them some code, right?
Yeah, we did say we are developers. So far, we haven't even opened up our IDE.
Yeah, so we need to fix this. So let me open an IDE. Here it is. So we will restart from the beginning.
Let's take a look at HTTP request. Let's take a look at the asynchronous request first.
So first, I need to start my microservice. So here will be the microservice A.
By the way, service A is running on Liberty.
Yep.
And service B is running on Quarkus.
Okay, so let's see if I have something. Yeah, I have something, but it's not yet ready. Yeah, okay. Let's start the Quarkus one. Okay, do we have it ready? Yes. Quarkus application obviously does quark. So it's ready, it's there. So the first demo we want to show you is using the REST client with fault tolerance. So Emily, can you tell us more about this code?
Yeah. So in this like service A directly connect with service B, we use the microprofile REST client to achieve a loosely coupled way to invoke the backend. And
you click on the wrong button.
Sorry.
Oh yeah, you cannot use the pointer anymore.
Yeah, okay. So in this way, like I make sure it's asynchronous and blocking. So asynchronous directly from microprofile fault tolerance, and you can see you can get a completion stage. So in this completion stage, I got an executor. This executor is direct from microprofile context propagation. So basically, this executor maintains some thread. All the threads you get from an executor have the right context associated with. So in this one, and then I have saying this timeout. If I don't get the Quarkus to behave within 1 second, I will fall back to a fallback method is called my fallback. So as you can see, like the line 44, that's directly my fallback method, and then I can return a response to the client instead of return an exception to the client.
So let's call this endpoint, right? Oh, I'm running on a callback, which it was.
See, it's a fallback straight away.
Oh, yeah. So it's actually working. So we have the fallback calling. Let me check if the Quarkus Cine is actually working. Yeah, no, should work. So there is some network Cine happening here. I don't know.
Maybe it didn't like my name.
Yeah, I probably like the name. But one thing we can do too, as I said, is that my microservice can misbehave. So here, I can actually ask him to fail once in a while for real. So what does it mean when it fails? It means that, well, the transmogrifier, which generates our password, is going to throw an exception saying that there is a quark. So once in a while, you will call this, and here we should have, yeah, the fallback. But as we didn't see it, the thing goes through. I don't know why. 19018, no. I don't know. Oops, sorry. Let's restart it.
Maybe we forgot to pray to the demo god.
Yeah, that's true. Is it done now? 8081. Let's go back to the IDE and not ready yet. No, we call it fallback every time. Anyway, we want to do this using reactive messaging. So
Yeah.
we will see if it works with reactive messaging. So how we are going to do that is we have started Kafka, and according to my machine, that's going to be interesting. So Kafka is running here. A and B are using reactive messaging to discuss with Kafka. So A gets a request, write it to Kafka, and B get from Kafka into this input channel here, and will write the output to the output channel here. In the code, there is no reference to Kafka, right? There is just some JSON object in, JSON object out, and we are just doing the processing here. So this signature here is returning a processor, reactive stream processor. There is in the spec more than 30 different signatures going to from very simple where you get a payload in and you return a payload back in a synchronous manner. Asynchronous manner, you can create your subscriber, publisher, and processor using your favorite library. You can also get the stream in as a publisher, as a flowable, as a flux, and do some manipulation and return the stream back. So you can really decide how you want to look like. So here I've decided to go for a processor because, well, it's relatively simple. A is going to send me a JSON object, and I'm going to do some manipulation of this, generate my password with my transmogrifier, and send that back in another channel. On the receiver side, so back to service A, I'm going to read from the output and store the result in a queue that I will be able to call using an HTTP endpoint. One thing I didn't say is how it's configured. Here it is. That's the configuration of my microservice B to read from Kafka and write to Kafka. So what do I have here? Well, I need to say where is my Kafka broker. So here it's running locally, so that's simple. But if you are on the cloud or something like that, you will just configure this, probably past username, password, and so on.
Yeah. So if you are on like the IBM cloud and you have IBM like event stream, then you can directly copy the broker address and directly replace with the connector. But for this demo, we use the local Kafka.
So, yeah, because Wi-Fi, it's always tricky to run on the cloud. Here we select the connector we want. So small y is a vendor, and Kafka is the type of connector. Obviously, there is Open Liberty Kafka that is also available.
Yeah.
Liberty Kafka, sorry.
Yeah.
And so on. So depending on your connector, the configuration might be a little bit different because even if there's the same protocol, we pick different convention. And here, for this one, I need to say that the channel input is going to use a deserializer getting JSON object, and a serializer getting JSON object to write it. If you're wondering what value serializer, value deserializer, that's just Kafka specific. So you go to the Kafka quick starts and you will see them.
Right. By the way, these all use micro profile config for this configuration to wire to the Kafka.
Yes, that's actually a good point. They're all using micro profile config to configure and so on. So let's start this. I'll try this. I need to Emily. Okay. Okay. This one is working. So what happened? I will try with, oops. We'll say Clément, for example. So it's going to write Clément into my Kafka topics. Microservice B will say, oh, there is a new message, get it, process it, generate my password, pass that back to my output topics. That will be read by my microservice A that will retrieve it and display it. Because it's asynchronous and HTTP synchronous, I may not have an answer yet because it needs to go to Kafka once, do some processing, and so on, and so on, and so on. So obviously, one time passed, I get my answer. I voluntarily add these oops messages. If you will have used completion stage instead of a synchronous call in our JAX serverless resources, it will display that immediately, but we will not have seen the asynchronous manner of this. So here we see that that's my password, actually. Oh, that's clear text.
Yeah.
That's probably not a good idea.
No, I know
anyway,
your password.
Yeah, well, let's check yours then. Who want to have its password display on screen? John, you want your password? Yeah. And John, here's your password. Sorry. Okay, so what did we build here? We built two microservices that are completely decoupled, even temporarily decoupled, using Kafka. We can have elasticity because we can have 1, 2, 3, XB. It's resilient. Even if B is not there, it will work. We have acknowledgement and so on. By the way, we didn't show it, but behind the scene of reactive messaging, there is also acknowledgement system. You can configure it using the @acknowledgement annotation or keep it the default that will acknowledge when the message has been processed correctly until the end of the chain. We have back pressure support because we have Kafka in the middle and reactive streams implementation. It's asynchronous. We have seen this. So I had to recheck my endpoint. And it's totally non-blocking thanks to the connector we are using. So basically, once upon a time, two reactive microservices.
Yeah.
And they live together happily ever after.
This is like a fairy land.
That's all we have. We have a few minutes for questions, I believe.
Yeah. By the way, we have the demos here if you want to check it out and have a play yourself.
So you can quark.
Questions?
Yep. You probably need to go to. Okay.
I know you were big on Vertex, right? So can you bring Vertex and microprofiles together if possible?
So the question is, what's the relationship more or less between microprofile and Vertex? Yes, I'm still part of the Vertex team somehow, and I'm still doing some stuff on Vertex. Vertex is a reactive toolkit for people that don't know this. And actually, the relation here is that the more reactive messaging implementation, the one I'm building, is based on Vertex. The Kafka connector you have seen is based on Vertex. And in Quarkus, starting next week, probably Monday, well, you know, release dates are always shifting a little bit, but probably on Monday, everything that is network related is going to be based on Vertex. So we are rewriting, we are in the progress of rewriting, we still have a few things that are not quarking correctly, but we are making it. So Monday or Tuesday, you will have a complete Quarkus application that will run on Vertex. You don't have to be Vertex expert to use it. It will be JAX-RS, it will be Servlet, it will be and so on. You could still use any Vertex API because we expose them. So it's up to you. You make your choice. Okay. Another question? Yes, here.
On Reactive Systems,
yep.
When the producer call on next function of subscriber, it passes the item, but the producer can't know when the item is not more used by subscriber.
So the question is, yes. So the question is, in the reactive streams, when you have a publisher that is calling on next on the subscriber, it passes the item directly. Actually, it cannot be null. It's forbidden by the spec, so it has to be an object. But yeah, there is no acknowledgement mechanism. So the only thing it can do is, if the processing fails, the subscriber can immediately cancel the subscription. But yes, you cannot reuse the object. There is no feedback to say, well, you can reuse the buffer, especially if you do I/O. Then yes, that is a little bit of an issue, and we are actually deep into it with a new version of Quarkus. But we found some way. So which SDK? In the Amazon AWS SDK, yes, they're using reactive streams, and sometimes you cannot reuse the object because. Yep.
Maintain buffer doesn't. I can't reuse
Yeah, it's not. You don't know. Well, you don't know when it's released. That's the problem. You have no way to know when it's released. So the overall idea behind it is normally what you try to do when you use reactive streams is to use immutable objects. So no byte buffer and so on, release things immutable. But I completely understand that sometimes it's not. Yeah, exactly.
Yeah.
Yeah.
So if possible, rely the reactive system APIs like reactive messaging, so that we can handle a lot. We have the acknowledgement built in, so we can handle that way.
So that's true in reactive messaging. We have acknowledgement back. So when I pass a message to my subscriber, when this message has been completely processed successfully, then I get an acknowledgement back, and I can release all the associated things. But that's a reactive messaging things. We are not at the network level. We are really a little bit higher. We are hiding all those details.
Mm-hmm. Great, thank you.
No, we don't have anything. Thank you. We'll be around if you have any more questions.